Hi, my name is Sylvia Brizzi. I'm a postdoc at the University of Texas at Austin, and I'll show you today the results of this work I've done in collaboration with my colleagues on the role of sediment thickness on subduction kinematics, and more specifically, the velocity of the subducting plate. And I'll show you that contrary to expectations, thick sediments might actually decrease the velocity of the slab. And I said contrary to expectations because we have now a range of geological, geophysical, and experimental observations that suggest that sediments are frictionally weak, and they also have high pore fluid pressure. This means that they might lubricate or weaken the megathrust, and for these reasons, they are thought to promote a faster plate speed. This has been recently demonstrated by Baer and Becker in 2018. They computed, using a semi-empirical formulation, the subducting plate velocity as a function of the interface viscosity for a range of interface shear zone widths. And they show that because of the higher viscosity of metabasalts, slabs with dominantly mafic rocks along the plate interface are slower than the slabs that are lubricated by the presence of sediments. These authors, however, caution that no simple relationship is expected in nature. And indeed, if we look at global observations of subduction zones, we either observe an inverse relationship between the amount of sediments and the convergence rate or subduction velocity, or we do not observe any correlation at all if we're looking specifically at the subducting plate velocity. So the question that I'm trying to answer is there any relationship between the amount of sediments and the subduction kinematics? And if so, do sediments make plates go faster or slower? And to answer this question, I'm using 2D numerical models. I'm using the seismothermomechanical modeling approach that has been developed by Van Dinter et al. 2013. We start from initial geometry, temperature distribution, and properties of the rock types, and we simulate long-term subduction by solving for the conservation of mass, momentum, and energy using a viscoelastoplastic rheology. This approach also allows us to simulate the seismogenic behavior of the megathrust, but for the purpose of this work, we've been only focusing so far on long-term subduction. Here you can see our model setup. We have an oceanic subducting plate, which is 40 million years old, and this plate subducts beneath an accretionary wedge and a continental lithosphere. On top of the subducting plate, we have included a layer of sediments, and we varied the thickness of this layer from 0 kilometer, so no sediments on the incoming plate, to a maximum of 6 kilometers. The boundary conditions are free sleep along the sides and the top of the model, while the bottom boundary is open. Subduction initiation is prescribed by this weak zone and by pushing the subducting plate at a constant rate of 7.5 centimeter per year in this small region. And since we want to investigate subduction kinematics, we stop pushing the subducting plate after 300 kilometers of subduction, roughly 4 million years, so that the slab can self-consistently subduct due to its negative buoyancy. Now let's have a look at some of the results, and here I'm showing you the average slab velocity as a function of time. And as you can see, as soon as we remove the push at 4 million years, we have this exponential increase of the slab velocity for all the sediment thicknesses that we have tested. What is more important, though, is that increasing the amount of sediments on the incoming plate actually decreases the velocity of the slab. And this is because including a layer of sediments on top of the incoming plate results in a different initial thermal and density structure of the subducting plate. Here I'm showing you the temperature as a function of depth for the 2N member models, so the one with no sediments and the one with 6 kilometers of sediments. And you can see how the temperature, for example, at the bottom of the oceanic crust is higher for the model with thick sediments. The density structure is also different at shallow depth because now we have this layer of sediments. So due to these initial differences, when we remove the push at 4 million years, the model with thick sediments have a higher temperature than the model with no sediments. So this means that the slab is warmer for thick sediments, and if the slab is warmer, there is less density contrast with the surrounding mantle. Hence, the slab pool is lower, and this explains why thick sediments decreases the velocity of the slab. So we tried and tackle this issue by exploring the role of the plate age. So we ran a new set of models where we kept the sediment thickness constant, and we varied the age of the subducting plate from 40 million years to 120 million years. And the reason we did that is because by varying the thickness, the subducting plate age, we are able to vary the thickness of the slab, and therefore take into account somehow the thinning effect that is given by a warmer slab with thick sediments. And here you can see from this viscosity plot how both varying the sediment thickness and the subducting plate age influences the thickness of the slab, which is something important for its velocity. To quantify better and to be able to compare our modeling results, we fitted the exponential increase of the subducting plate velocity as soon as we remove the push, and we use the B coefficient of the exponential function as a measure of how fast or how slow the slab is moving. And I'm plotting this B coefficient as a function of both the sediment thickness and the subducting plate age. So what we see is that increasing the subducting plate age results in an increase of the velocity of the slab, and this is what we expect because the slab is thicker, it's colder, there is more slab pool, and therefore the slab can subduct faster. Irrespective of the plate age, however, if we increase the amount of sediments on the incoming plate, we are decreasing the velocity of the slab. And this decrease seems to be much higher for the older plates than for the younger plates. And it also seems that there is a sediment thickness threshold after which the velocity of the slab doesn't decrease as much. To better understand why sediments are slowing down the subducting plate, we looked at the shear stresses along the megathrust, both at the shallow and the deep megathrust. So here I'm showing you the second invariant of the deviatoric stress tensor for our 4N member models. And what we did was to extract the shear stresses within each of these polygons, to integrate them and then multiply them by the length of the polygon, because you can see how these polygons have very different lengths. So this is what I'm plotting here, the integrated shear stress within the polygon times the length of the polygon for both the shallow and the deep interface. So if we increase the amount of sediment thickness on the incoming plate, we observe an increase of the shear stresses at the shallow interface, independent of the plate age. And this is because increasing the amount of sediments promotes the development of a big accretionary wedge. If we look at the deep interface, the relationship between the shear stresses and the sediment thickness seems to depend on the plate age, because we observe a decrease of the shear stresses for plates that are younger than 80 million years old, and we observe instead an increase of the shear stresses for older plate. If we now look at the sum of the shallow and deep interface, so shear stresses along the overall megathrust, we observe this stress sweet spot between models with thin sediments and young plates and models with thick sediments and older plates. For these models here, however, we can see that the megathrust has high shear stresses because of the contribution of the deep interface. And if we compare this outcome with the B values that I was showing you before, we see that there is a lack of correspondence, meaning that Models with thin sediments and young plates have a high shear stress along the megathrust because of the deep interface, but they also have a higher velocities lap velocity compared to the models with thicker sediments. So this suggests that it's the shallow interface that it is influencing the subducting plate velocity. So as we increase the amount of sediments on the incoming plate, we're building up a bigger accretionary wedge that increases the load at the shallow megathrust, and therefore we observe the high shear stress at the shallow interface. But if the shear stresses are high, this also means that the resistance to subduction is high. So the main result of this work is that, yes, sediments are frictionally weak and viscously weak, but they might build a very wide accretionary wedge that influences the kinematics of the subducting plate. So this means that rheological properties might not be the only control on plate kinematics. There are other questions now that needs to be addressed. So it's important to understand how both the sediment thickness and the properties of sediments affects the plate motion, and also what are the conditions that might promote the development of a big accretionary wedge. So that's it. I look forward to meeting you all during the live session, and thanks for joining.